Good morning, everyone. Today, I am going to deliver a presentation on the fold mechanism. So, I will start from the introduction. So, folding is influenced by the orientation related to the layering rock rheology, which is related to the mechanical behavior of a rock and kinematics movement pattern during the deformations. If we talk about the folding is a fundamental rock deformation response. To understand fold formation, we need to look at three main factors which I have discussed, like orientation of a stress relative to rock layers, the rheology or a deformation behavior of the rocks, and kinematic, which is movement pattern during folding. There are the three key fold mechanisms based on the stress direction, which is parallel to layering like buckling, across layering such as bending, shear related mechanisms like flexor slips or simple shear. If we talk about additional fold can be classified as active fold where rock layer resists deformations and passive folding where layers simply record strain without resistance. The most important distinction is the active folding. Layer is deformation due to the viscosity or a competence contrast, and passive folding. Layer flows with surrounding rock and serve as a strain marker. Fold mechanisms include layer parallel shearing, orthogonal flexor slip, flow, and simple shear and kink and several folding mechanisms. As you can see from the image in figure in which we have seen the how buckling, bending, and passive folding occurs, how their stress orientation different from each other. Let's move to next slide. In which buckling, buckling is a classical example of active folding and happens when where a competent layer, which is a high viscosity, is shortened parallel to its layering within a less competent matrix. It results in the development of rounded sinusoidal and parallel fold like class 1b geometry. If we talk about the this result in this, as I can discuss about the fold type and preservation of the layer thickness, fold within the periodic wavelength where wavelength to thickness L by H ratio stays constant in deformation loculi within the roughly one wavelength. In multi-layer sequences, competent layers show class 1b. Incompetent layer development, other fold types like class 1a or 3. Hinges tend to be cusped and point towards competent layer. Let's, as I've discussed about the buckling, next is the passive folding. In passive folding occurs when layering has no mechanical influence on a fold development. Passive folding happens the layered rock has little or mechanical resistance, acting as a strain marker rather than actively resisting deformation. These folds reflects ductile strain patterns rather than mechanical contrast, often form class 2 fold with similar geometry, developing during the coaxial transpiration or sub-simple shear. Are common near shear zone faults, monomineralic shear zones. It can form in different, as I have discussed about, it can form in different sub-simple shear, coaxial, transparent. It reflects infinite spectrum of kinematic model that involve ductile flow. Can be found in ductile deformation, common in shear zone, especially in monomineralic rock. Rack folds along fault brittle rhythm may show passive geometry. As from the as As from the image, we can see different in simple shear passive folding and pure simple shear passive folding can be seen in the diagram. Let's go to this bending. In bending occur due to the stress acting across the layer, commonly from external forces like basement fault movement, intrusion such as magma, salt diaphragm, differential compaction basin, and bending involve multiple deformation processes such as flexor slip and simple shear. The triaxial model is often used to explain folding in fault-related bending, especially where strain localized in triangular zones ahead of fault tips. Fault tips and model bending can be understood by different like simple shear model and triaxial tri-shear models. Example as from the image we can see example of bending in various settings between boardings, above thrust ramps, or reactivated faults, or above shallow intrusion or salt diapers. And if we talk about the flexor slip and flexor flow model, two important kinematic folding models are flexor slip and flexor flow. In flexor slip, in flexor flow occurs in the ductile layers where shear strain is distributed continuously through the fold limbs. No distinct slip surfaces on neutral surfaces can be seen, and shear strain increases with limb rotational and deep angle, also result in class 1B folds. If we talk about the flexor flow, it occurs when shear strain is distributed homogeneously within the ductile or weak layer. There is no formation of slip surface, neutral surfaces, and it goes through plastic deformation. In neutral surfaces, we get to see increasing strain away from hinges. It is formed in plastic resin and it is shear strain related directly to layers rotation. The opposite shear sense can be seen either side of the axial plane. It forms 1B type of folds. In orthogonal flexor class 1B, it is also known as tangential longitudinal strain. Tangential longitudinal strain. It has lines which are originally orthogonal to layering, remain orthogonal throughout deformation. It forms parallel folds with neutral surfaces which show outer arc is going through extension and inner arc is going through contraction. It can be seen stiff competent layer that resists ductile deformation. We make strain lifts the long the long axis is orthogonal to bending in the inner arc and parallel to the bending in the outer arc. In tight folds, orthogonal flexor transition into flexor slip or flexor flow due to the increased strain. As from we can see that the images from the image we can see how flexor orthogonal flexor and flexor flow can be formed. If we talk about the at last we have king bands and chevron folds typically form an anisotropic laminated rocks like slates or phyllites. There is a layer shortening in low grade metamorphism condition. These form class 2 type geometry folds, similar folds, but it can be distinguished by their symmetry and hinges. If we, do, if we take if we talk about the king bands, narrow zone with sharp foliation rotation, often asymmetrical, occur under low-grade metamorphism and may form conjugate sets oblique to shortening direction. Chevron folds, angular folds with straight limbs and sharp edges, usually symmetric, formed by the flexor slip during the layer parallel shortening, or common in sequences of alternating competent and incompetent layer. From this, we can conclude that from the summary that fold form when layered rock undergo deformation under stress. The mechanism of folding depend on the stress orientation, rheology, and competence contrast between layers. In an active folding, mechanical contrast between competent and incompetent layer play a dominant role, while passive folding involves layers that merely record strain without influencing the fold shape. Bending driven by external forces acting across layers shows how geometry and boundary condition control deformation, often resulting in complex folding scenarios such as fold bend folds or forced folds. And flexor mechanism like slip, flow, orthogonal flexor demonstrate how folding accommodates strain while preserving layer thickness. In kick, if we talk about especially about the flexor slip and flexor fold, folding are dynamic model depend on the rock brittleness or ductility. In orthogonal flexor preserves a geometric relationship in open folds, but it's replaced other mechanism in tight fold. Kick bends and chevron folds form sharp structures in anisotropic elementary rock controlled by the layer properties and deformation condition. So this is my summary and this is my reference, and thank you.